Now, let me put in one this thing. Okay, can you see this? It is the global number of child deaths from 1990. 1990 for you may seem quite a long time ago, but for me and for Sadish and all that, it seems quite recent, and it's actually quite recent in terms of human history. But you look at a difference even from 1990. See, 1990 we had a lot of vaccines. Most of modern medicine was quite well developed by 1990. But from 1990 to 2017, parts of the world which were not covered by vaccines and not covered by primary health has come under primary health cover, even though the population must have increased at least by 1/3 or so. So even then you see the improvement, and the bulk of the improvement has come from preventing vaccine preventable diseases like tetanus, whooping cough, measles, meningitis, diarrheal diseases, acute respiratory infections, etc. Now, if you look at polio, I'm sure you wouldn't have seen many people with polio or a residual, so-called post-polio residual paralysis. But when we were doing our school, lot of people, lot of boys in each class of 100, at least one or two, or many in some classes, had post-polio residual paralysis, because it is a devastating disease. If you do not die by polio, of course, a lot of people recovered, but it was a flu-like illness which used to affect a lot of children, especially children, and a substantial proportion of them became totally paralyzed for some time. And then they had variable recovery. So it was a terrifying disease, because once you have the paralysis, you don't know how much you will recover. Over a course of months, many people will recover completely, but many people might not. See, both of your legs might be permanently paralyzed, or your hands and legs might be paralyzed, things like that. Now, if you look at from 1980 onwards, from 2015, polio is a disease which is almost eradicated, almost. And the same is the case with mumps, measles, rubella, and many other diseases. Of course, we do have challenges still. And most of you may not even have heard of smallpox, a case of smallpox. Even I haven't heard a case of smallpox. I don't remember, because smallpox was eradicated by 1980. WHO has said that, announced that smallpox is eradicated by 1980. And it was arguably the most dreaded viral disease, or even most dreaded disease ever to affect humanity. It used to kill off 500,000 people in Europe alone per year when it was at its peak. And it is, I don't know, it must have killed at least, they say, 500 million people if you look at the whole of human history. But now it is no more there. Now, when you look at, before we going into the vaccination part, I'll just kind of reiterate or recoup, or we relook at what we learned last class. We said that whenever a pathogen, which is a virus or a bacteria, enters our cell, our body tries to attack it and kill it and prevent infection, prevent disease. And this is called immunity. And there are innate immunity and adaptive immunity. In innate immunity, various cells in our blood and in our tissues will attack it, bombard it with chemicals, and even eat it up. In adaptive immunity, what happens is that there is a thing called antigen. Adaptive immunity is specific. It is, for example, it is specific for smallpox. It is specific for COVID. It is specific for any of the infections. What happens is that if the innate immunity is not able to stop the infection, antigen presenting cells, like dendritic cells and certain B cells, etc., will take out or degrade the pathogen, present parts of it, which are usually proteins, and these are called antigens. And with this antigen in the walls of their cells, they will run through the lymphatic system to the lymph nodes, where a lot of cells, immune cells, are waiting. This is the intelligence wing of the immunity, which is adaptive immunity. There are lymphocytes, which are B lymphocytes as well as T lymphocytes. Now, B lymphocytes, what they do is that they'll take in the antigen and produce antibodies against it, which are certain chemicals which can bind and destroy the cells directly, as well as make it more easier to kill by other cells. That is what B cells do. Now, T cells also recognize the antigen. Then they differentiate into CD4 T cells and CD8 T cells, just like B cells. They also multiply and they directly attack these cells. It is not important to know the exact details all that much, but you just should know approximately what is happening. Now, initially, even I used to think why this B cell and T cell, why this difference? B cell is called humoral immunity, T cell is called cellular immunity. Why? Because see, B cells are able to recognize antigen in solution. Antigen in solution, in the blood, in the tissues. Okay, naked antigen. But T cells can only recognize if it is presented by the antigen presenting cells. Okay. Now, why this is important is because many of our pathogens are not in the tissues or in the blood only. They get into our cells. And they can grow inside our cells. And viruses are the most important pathogens which belong to this group. So viral immunity is very much dependent on this cell presentation. Okay. Only when they are presented, the immunity can act. And that immune cells have to attack our own viral infected cells and kill that. Okay, so what's the main difference between virus and a bacteria? Bacteria can get in, or even fungi, fungus, and other pathogens. They get in and they can directly multiply by its own in our body. But a virus, for example, our COVID virus or a flu virus, what happens? It is just like a information. That's why, computer virus, we say computer virus. Just like computer virus, it is a piece of genome. It's a piece of information. It gets into our cell. It cannot divide on its own and uses our own cellular mechanism to produce its own kind. So how does it do that? See, viruses are of two types, DNA viruses and RNA viruses. Now, DNA viruses will get into our cells, go into the nucleus and get integrated into our DNA and then express itself to produce more of it. Okay, but if it is an RNA virus, there are two ways of doing it. One is that RNA virus can get into our cells and directly create RNA in the cytoplasm without going into the nucleus by acting as an mRNA and creating in the process a kind of enzyme called RNA polymerase 2. I mean, RNA polymerase 2 means TOO2, RNA polymerase. And that RNA polymerase can directly amplify the virus. It will just multiply this RNA strand which is made by our cellular machinery, and the whole cell will become totally full of viruses. And that is how it produces disease. Then there are the COVID is like that. But then there are certain viruses like AIDS virus, which will using a reverse transcriptase enzyme will produce its RNA virus will come into the cell then it will cause its own DNA to be, corresponding DNA to be produced, and this DNA will get into the nucleus and produce, RNA. So the details are not important. What I am saying is that you should know how, approximately how viruses infect us and cause disease. Now, what does vaccination try to do? Why was vaccination so important, or why is vaccination so important, especially for viral diseases? Is that for bacterial diseases we have a lot of antibiotics which are very effective when compared to viral infections. Of course, we do have antivirals like antibacterials or antibiotics. We have antibiotics against viruses too, like which are called antivirals now. In the past few years or a few decades, we did not have previously, but they are not as effective as antibiotics for bacteria. So it's very important to prevent viral infections by vaccination. So in vaccination, what are you trying to do? From early on, people sort of realize that once you get a severe viral disease, some of the viral diseases you can get again and again. For example, influenza, flu, common cold, and all that, you will get again and again, but not immediately. You will have an immunity for a certain period of time, but after that you will again and again get it, because these viruses keep changing their shape, and they mutate into a different form, so that our immunity does not recognize it. But certain severe viral illnesses like polio, like smallpox, like chickenpox, and many other viral illnesses, once you get the disease and you recover from it, you will not get the disease again, or even if you get it, will be very mild. Why is that? Because it has elicited an immune response in us, and that memory cells are there. So when they come again, immediately either the antibodies are already there in the blood against it, which will attack it, or these cells will recognize that same virus. This is the smallpox virus which attacked me last 2 years back. Now we can easily produce antibodies and cytotoxic and helper T cells against it, and immediately it will mount a very robust or strong immune response and kill it off, so that you will get a very mild disease or no disease at all. And many a time this is lifelong. So people realize from early on that once you get smallpox, see, for example, smallpox, I told you, smallpox was one of the most important and terrifying viral infections of mankind. So during Middle Ages, and from probably from thousands of years, smallpox has been there. And people recognize that once you get smallpox and recover from it, 30% used to recover. It had a huge death rate. 60 to 70% people died if you contract smallpox. Many became scarred for life, and many became blind because the vesicles and pustules used to scar the eyes, and they used to scar the face and create ugly marks, much more than chickenpox. You might have seen chickenpox scars, but never smallpox scars. Smallpox scars used to be horrible, and a lot of people had smallpox scars in those days, because 30% only used to recover. But once you recover, people notice that you will not get smallpox again. So it from a very old time, thousands of years back, people must have started deliberately using the fluid from smallpox blisters. There is that blister caused by when you have smallpox, there is a blister in the skin, and that fluid, once that the disease is almost gone, they'll take a little bit of this fluid, then put a small scratch on a healthy person, and then introduce the fluid there. Or what they used to do was that once they in China in 16th century and 17th century, in China, even in India, they said they used to do it. They used to do this practice, which was called variolation, not vaccination, variolation. They used to take out the scabs from the healing ulcers and create a small piece of powder or something like that, and then blow it into the healthy person's nose, or they used to create a small scratch in the skin and then try to introduce it. And they usually get a milder disease. This is a natural attenuation process. That is because once the disease is dying down in a person, we don't know now. We don't know why the variolation used to work, or why the variolation did not produce a severe disease in all of them. People getting being variolated, but it must have been that the virus in the people who are, the dying down phase of the disease might have been a weakened virus. Nowadays, we have live attenuated vaccines similar to that. So it used to create a mild illness in people. And then that used to completely prevent smallpox from coming again. But it is dangerous because 3 to 4% used to die from this in this variolation induced smallpox. So it is a dangerous thing, but still it became enormously popular all over the world and including Europe for a century or so, because smallpox was such a dreaded disease. So this risk people were willing to take. And that was the situation till Edward Jenner in 1800s. 1700s. A physician called Edward Jenner noticed that there was he did not notice actually in the English countryside, people were talking. Okay, there was a myth, there was a tradition that milkmaids usually do not develop smallpox, and their faces are very pretty always because there is no scarring. Milkmaids don't have smallpox, they never get smallpox. So that was the myth going around the countryside. Everybody sort of used to say this. They never got smallpox. And why was that? There was a disease called cowpox in cows, which was a mild disease. So milkmaids, when they were milking cows, used to get this cowpox. But it was a very mild disease and which will cause blisters only in their hands. But once they get cowpox, they will not get smallpox. Why? Because it was a related virus. And once your body mounts an immunity against cowpox, there will be a cross immunity against smallpox. So this is what Jenner did. He deliberately introduced cowpox to people. And then he found that variolation did not cause mild disease in them. Then he became bolder. Then he gave them cowpox, and then he gave them full dose of smallpox, but no one got the disease. Of course, it is difficult to do such kind of tests now because it will be unethical and nobody will agree to it. But that time he did, and he found that it was very effective. Nobody got smallpox, and that he named vaccination. But you see, you should remember, that time nobody knew that microorganisms existed. So no one knew how it worked, including Jenner. We will just fast forward the whole thing to 100 years later, and this man is called Louis Pasteur. A lot of things had changed by that time. These 100 years, it was the 1800s, okay, 1850s and all that. Louis Pasteur was a chemist. By that time, the microscope was invented by Leeuwenhoek, and then people were looking everywhere they could find microorganisms. People were starting to suspect that some things were caused by microorganisms. Some said that, okay, these contagious diseases could be caused by microorganisms. Some said putrefaction, or the way the the food or bodies of animals became bad and rotted was due to microorganisms. But many people that time thought that it was just chemical dissolution and fermentation of alcohol. I mean, sugar into alcohol. This also was thought to be a chemical reaction. But Louis Pasteur was the first person to systematically demonstrate that fermentation and putrefaction were by microorganisms. Then he went on to theorize that microorganisms might be causing disease. And then he succeeded in culturing microorganisms and did studies. And then Robert Koch, another German king. So Louis Pasteur was in France. Robert Koch was in Germany. That time there was an Franco-Prussian war and all that. There were severe rivals, not like today. You think entire Europe is a united place and everybody is friendly and all that. That time there were commerce happening. There were exchanges of information happening, but they were also fighting with one another. There were severe. Robert Koch and Louis Pasteur were severe rivals. But what both of them did was to create a foundation for both vaccination and microbiology. Together, they found that they could culture most microorganisms in the laboratory, give it to animals, and study them systematically. And they deliberately made vaccines. For example, Louis Pasteur, he was the person to discover vaccine against rabies. Rabies was a very dreaded disease. From dog bite we get rabies. And Louis Pasteur found that, rabbits could be infected with rabies. Rabbits. Then he found that the microorganisms he inferred, of course, he couldn't see viruses that time. We could not see viruses that time. But he inferred that the rabbit brains were the most infectious part of or spinal cords also were the infectious part of the rabbit. Then he found that if he dried out the rabbit's spinal cord, he could make a small vaccine. He could make it, dried up the spinal cord and then ground it up and made it into a solution and then injected it into animals. He could prevent it from happening. Then he was forced to test it because a doctor referred to him a boy, Joseph Mister, was heavily bitten by a rabid dog. So that time, a horrible death was inevitable once you had that. So Louis Pasteur was forced to try it out, and Joseph Mister never developed rabies. And Joseph Mister, there was even before Louis Pasteur died, there is a Pasteur Institute in Paris, which is one of the most famous institutes of microbiology ever. Even now it is there. And Joseph Mister was a gatekeeper in that institute till he died. So interesting, isn't it? So when you have types of vaccines right now, what are the types of vaccines we have? So we are trying to introduce the antigen without the healthy person getting the disease. Okay. We are trying to introduce the antigen without the healthy person getting the disease. So you have to inject a part of the virus or bacteria into the living healthy person, isn't it? There are various ways of doing it. You have live attenuated vaccines like this cowpox, which we told you, but no longer used. You have tuberculosis, this oral polio vaccine. Then we have measles, rotavirus, yellow fever vaccine and all that, which are weakened viruses. Okay, they are live viruses, but they are weakened. They cannot cause disease. They cannot cause disease, actually speaking, but they will mount an immune response. An antibody response will be generated, which will prevent infection with the disease. Then we have inactivated viruses or a killed virus or a killed bacteria. And then various adjuvants will be added and solution and drug or medicine will be made and injected. These two are the traditional method of making vaccines. Then there is a subunit vaccine. That is, it's a purified antigen alone you are giving. For example, for SARS-CoV-2, you can take only the subunit, that spike protein, which attaches itself to humans, and take that alone and inject it. That will produce an immune response, but usually no, it will be weak response. Then there are things like toxoids, which are antibodies against the toxins produced by the microorganism, not the microorganism per se. For example, tetanus toxoid, or the TT, which we take, is a toxoid. I'm not going into the detail of that. Maybe if we want, we can take questions. But very, very generally, what we have is a live attenuated vaccines, which are live vaccine. I mean, live viruses, which is a weakened live virus or bacteria. It is made from that. Then you have inactivated or killed virus or killed bacteria. From now on, I'll say virus, because we are talking about maybe COVID, because that is what we are interested. I mean, we are seeing in the media right now. We are in the middle of a pandemic, although it's in the dying stages. The pandemic is now inactivated virus vaccine means it's a killed virus. Okay. Then we have brand new methods of creating vaccines. And many of our new COVID vaccines are made like that. These techniques are developed only in the last few years or even 1 or 2 decades. You don't need the virus at all. You can have the virus's genetic material alone. You can sequence it in the laboratory. For example, the genetic sequence coding for the spike protein of the COVID virus. Okay, just the spike protein gene, that stretch of DNA we can take. And then we can put it in a virus vector. What's a virus vector? It is usually an adenovirus or a common cold virus. For example, our Covishield is a chimpanzee adenovirus vector vaccine. So what they do is put a small piece of DNA, which is coding for the spike protein of CoV-2, and put it into the chimpanzee adenovirus, which is just a carrier. It cannot cause human disease, and it cannot the parts of the genome that can cause division is taken off the chimpanzee adenovirus. So we can do all that now. We can do precision manufacture of organisms and genomes. So we can take out these genes from the adenovirus, then attach this spike protein DNA, and then introduce it into a healthy human being. Then what happens? This adenovirus can fuse to our cells, and it can introduce the DNA into the cell. And that cell will produce the antigen. So we are not introducing the antigen. Our own cells will produce the antigen using our own machinery, and then express it in our cells. So antigen presenting cells will express it. So that is the basis of a DNA vaccine. Okay, we can even use naked DNA as a plasmid and then introduce it into our cells. This is a very brand new technique, and virus that there are till now no vaccine produced by that method. But then there is the mRNA vaccine, which is the Pfizer vaccine, which is which came first, actually speaking. I mean, one of the vaccines which came first and were widely adopted all over the world, but we did not have it. The mRNA vaccine is very interesting because it does not use any viral vector or anything. It just uses that mRNA which codes for the spike protein and then coats it in a totally artificial lipid membrane. And then that is what is being injected. So each lipid ball will contain thousands of small mRNA particles, and that lipid ball will balls will go, very microscopic lipid balls will go and fuse with our cells and introduce the mRNA. The mRNA, even without going into our nucleus, will start producing in the cytoplasm, along with the ribosomes of our own body, will start producing the COVID antigen, the spike protein, and it will be presented in the immune cell surface, and it will trigger an immune response. So this is, I hope you understand how this happens. Okay, these are all the same thing, viral vector. And now if you look at mRNA vaccines, our Pfizer and Moderna, you would have heard all these kind of terms. These are all company names. Pfizer vaccine, Moderna vaccine, or mRNA vaccine. Our Oxford AstraZeneca vaccine, which is our Covishield, is a viral vector vaccine, DNA vaccine with a viral vector. Then you have inactivated virus vaccine, a traditional type of vaccine, which is our Covaxin. Then Sinopharm and all that. And protein-based Novavax is there. And newer vaccines are coming up. And as you know, we may be in the dying stages of the pandemic. Of course, COVID may not go fully from our lives. It may continue because it will become an endemic virus, usually like a flu virus. That is what we think. And we are seeing the fag end of the pandemic, hopefully. And the rapid development of vaccines really helped. You just cannot, you have to realize that the very rapid, within 1 year, all over the world, scientists and researchers and technicians all over the world has succeeded in developing a vaccine for COVID and then start administering it within 1 year, which is a remarkable achievement because no vaccine has ever been made. It usually within 5 to 10 years, less than usually 5 to 10 years, it will take for a vaccine development. Of course, this is stages of vaccine trials. Whenever a new vaccine or a drug is now made, you just cannot kind of like Edward Jenner, just cannot take people and then inject it into your neighborhood kid and then just see whether he's developing the disease. Not like that. It has to go through a lot of studies. First, it has to be studied in a cell cultures. Okay, whether how it reacts, how the cell reacts to the vaccine or the drug. Then there is a phase 1 study where you just take around 5 to 10 people, volunteers, healthy volunteers, and then inject it into them and just see, are they developing side effects? Are they developing antibodies? How effective it is? What is the effect of it? All that. And if it's a drug, it's not a vaccine, it's a drug, we will find out the pharmacokinetics of it, pharmacodynamics of it, because how it is, when is it coming up in the blood, what time it takes for it to get its maximum saturation in the blood, when is it eliminated, things like that. And then phase 2 happens, where you inject it to maybe a few hundred people. Okay, a few hundred people, and which are not healthy volunteers, need not be healthy people, just a population sample. We will inject it, and then you will see how the same things, how many develop side effects, are there any other effects, is antibody developing, and again these pharmaco and the dosages and all that are calculated at this stage. See how much dose you have to give, things like that. And then in phase 3, you take thousands or tens of thousands of people. For example, maybe 30,000 or 40,000. The Pfizer vaccine in the phase 3 trial had 43,000 participants. But the phase 3, you divide the study group into two randomized groups. And for one group, you give the vaccine. For one group, you give a placebo, which may be saline or some dummy shot. But nobody will know. It may be double blinded. Even the people getting the shot will not know whether they have got a vaccine or the placebo. And even the researchers who are looking at the results will not know which group they are studying. There is an oversight authority which looks at it. So this is called a double-blind trial. Then it is compared and that efficacy is calculated. So there, in case of COVID or something like that, what they have done or what we have done or what we have to anyway do is after the vaccination, after phase 3, both groups are let loose in the population. And then after 2-3 months or periodically, you see how many actually develop the disease. That can be taken as one endpoint. Okay. For example, if, you have 1,000 people with the vaccine, 1,000 people who got a placebo. Now, when after 3 months, you find that out of 1,000 people, 100 people got the I mean, 100 people got, out of the placebo group who did not get vaccine, suppose 100 people got COVID. And out of the 1,000 people who did get the vaccine, suppose nobody got COVID. Then you can say that this is 100%. This vaccine has got 100% efficacy as per this particular trial. So it's a relative risk assessment. So this is how they say, okay, it is 90% effective, 60% effective. But again, you have to look at another way. See, when the Moderna or the initial Pfizer vaccine and the Moderna vaccine was studied, it came out that it was 90%. It had 90% efficacy in preventing symptomatic disease. But when the Johnson & Johnson vaccine came and when the Covishield and Covaxin, especially the Covaxin, was a little bit late, and then when you do the phase 3, you say that it just got only 60% or 70%. Doesn't really mean that they are inferior. It's a fine point. What I'm telling you is that you have to be careful in interpreting the results, and when you should understand that there is some subtleties to it. You should know all the statistical fallibility, because when the Moderna and the Pfizer came, the most of the places where it was tested, the COVID was at its peak. And later when it was tested, most of the time the transmission was not so strong. And this kind of effects, and plus the virus must have mutated quite a bit. So new variants had come, which had immune response by the time phase 3 of these vaccines were coming. So naturally their efficacy will go down. So a lot of these kind of things are there. Because what we have today, what I have talked to you today is, why are vaccines important? What is immunology? Again, we have just immediately recollected what we have taught last time. And then the brief history of vaccination, Jenner, cowpox, Pasteur, Robert Koch, rabies. All right, don't forget all these. And then we have found how vaccines are made, types of vaccines. There are attenuated or weakened virus, killed virus. Then there are the newer vaccines, DNA for spike protein, in an adenovirus vector, then mRNA vaccine without a vector. Okay, all right, that's it. Now we can have questions.
Sir?
Yeah.
Nowadays, if we get COVID, if we recover, we may have the chance of getting it again, because it's constantly like evolving. Why can't viruses like smallpox and chickenpox, etc., uh, come up with new variants like that?
That's a good question. That is a little bit, that has got a little bit to do with the inherent property of the virus. Because a smallpox, there is only a particular, um, window or a particular range in which it can mutate and remain infective. That is the difference. If a smallpox or a chickenpox viruses, it mutates a bit, then it cannot function. It is like that. And that is the reason why these vaccines are more effective against it. And the mutation rate, we are not worried about that much. But it can happen. For example, the polio is not completely, we are not able to eradicate, because a lot of people from the field are saying that the polio virus is slightly becoming mutated and becoming resistant to present vaccines. And that is it can happen. It is happening, but not like many other viruses, especially those viruses which cause mild disease. Like COVID is now become a mild disease mostly. If it was a mild disease for most people, and some of the viruses like this coronaviruses, like this COVID, then influenza, and some these, you do not get permanent immunity to these viruses, because they can mutate quite a bit and evade our immunity. This is a type of evolution happening in these viruses.